In the late 1930s, the Union Pacific had introduced its new Challenger locomotives to the main line over the Wasatch Range between Green River and Ogden. With a total of 12 driving wheels, these engines were equipped for running up and down most of the grades present on the line. However, the eastward grade from Ogden to Wasatch was still too steep for these engines, and as such, the trains would have to be double-headed to complete the trip. The Union Pacific wanted one engine alone to be able to make the trip, and so rather than running shorter, more frequent trains, they decided to double down and make the engines bigger. The American Locomotive Company was tasked with building these engines, and decided to base the new designs on the currently operating Challenger locomotives. They found that by simply making the firebox bigger, increasing the boiler pressure, decreasing the size of the driving wheels, and adding an extra 2 wheels to each set of driving bogies, they could fulfill Union Pacific's needs. Given the sheer size of this 4884 design, some aspects of the locomotive were simplified, with compounding booster and feed water heaters being taken out, and the standard Baker valve gear being swapped out for good old-fashioned Volschwerts. The Challengers were already big enough engines, but the changes put in place to create these new locomotives made them even bigger. The engine alone of these new designs was 85 feet long, roughly 10 feet bigger than the Challengers. They were also 11 feet wide, 16 feet tall, and weighed 350 metric tons. To call them big would be an understatement, especially as they currently hold the record for the biggest steam locomotives ever built in terms of both weight and length. Supposedly, these engines were going to be classified as Wasatches, after the mountain ranges they were built to work on. However, an unknown employee of the American Locomotive Company chalked the words "Big Boy" onto the smokebox door of number 4000 while it was under construction. Most workers found the name humorous, and it stuck as a result, leading to the entire class of engines officially being known as the Big Boys. When they finally came into service in 1941, they were more than equipped for the work they were built for, easily hauling the heavy loads they were given up the steep and unforgiving grades of the Wasatch line. During service, their rated haulage tonnage was increased several times, as it was found that the engines were actually more powerful than the Union Pacific first realized. Despite their capabilities, the Big Boys normally operated well below 60 miles an hour while in freight service, being designed with a wide margin of reliability and safety. Footplate crews also held the Big Boys with high regard, as they were reliable, sure-footed, and very user-friendly. The only real problems the Big Boys had were their awkward size and their appetite. Just like many of the other massive engines running on the Union Pacific, their sheer size made shunting difficult, though not impossible. The amount of fuel they burned was also quite excessive. They mostly ran on low-grade coal, and as such required more of it to fire consistently, with a Big Boy on average burning 11 tons of coal an hour while operating at full power. Union Pacific tried to save on fuel by modifying number 4005 to burn oil in 1946. However, the experiment didn't work out, and it was converted back to burning coal in 1948. Despite their reliability and power, the Big Boys only remained in service for little over 20 years due to the sharp increase in coal and labour prices after the war, and the introduction of much cheaper to operate and maintain diesel-electric engines. The last revenue-earning train pulled by a Big Boy ran in July of 1959. All of them were put into storage, but the last wasn't officially taken out of service until 1962. Unsurprisingly, many have been preserved, with 8 still remaining out of the 25 built. 7 are currently on display at various museums around the country, with number 4014 being restored in 2019 and running various excursions to celebrate the 150th anniversary of the first transcontinental railroad. All in all, the Big Boys somewhat represent the last hurrah of steam locomotion, not only being the biggest steam engines in the world, but also really pushing the limits and showing what steam power was truly capable of. Just goes to show that sometimes the right tool for the job isn't always an overly engineered machine. Sometimes all you need is just one big boy. In 1905, the Chemins de Fer du Nord of France were in need of some new engines to haul heavy coal trains, which at the time had to be double-headed. Naturally, engineer Gaston Dubosquet felt that an articulated locomotive design would do the job. However, most articulated designs at the time had their drawbacks. Mallet designs didn't quite have the articulation he desired, Meyer designs may or may not have had issues with their fireboxes, and Fairley's were proving to be fairly problematic. As such, Bousquet took it upon himself to design his own unique engines. Introducing the Du Bousquet locomotives. First built in 1905, these engines used a similar wheel arrangement to Meyer-type designs, having two articulated bogies mounted under the boiler with the cylinders centered towards the middle of the frame. Each bogie had 6 driving wheels powered by 2 cylinders, making for 12 driving wheels in total. As the cylinders were so close together, it allowed the front set to connect to the rear set, with the rear set being powered using high-pressure steam which then flowed to the front set, which were designed to operate using lower pressure steam. A gap was left in the middle of the locomotive's water tanks to allow easier access to the cylinders for maintenance, and the unpowered wheels helped support the cylinder's weight. The main difference between the Bousquets and typical Meyer designs was its rear bogie. Most Meyers tended to use more rounded, spherical joints on both bogies, which did allow for better articulation, but the complexity of the joints required complex flexible pipes to connect the boiler to the cylinders, which were prone to leaking. Bousquet's design, on the other hand, used rear bogies that only rotated left and right, making it much easier to design joints to pipe steam from the boiler, with the front bogie still using a more rounded joint to provide extra flexibility. 48 of these engines were built between 1905 and 1910 for the Chemin de Fer du Nord, and put to work pulling heavy coal trains along the steep gradients of the lines of northern France. Not only were they capable of moving the loads, but were also able to do it at speeds of nearly 60 kilometers an hour. Seeing their success, the East Railway built an additional 13 for themselves between 1910 and 1911 for goods work. By 1921, however, it was decided the engines were better suited elsewhere, and 34 of the Nord's engines, along with all 13 of the East's, were moved to the Grand Ceinture line to move freight around Paris. An additional 38 Bousquets were built to help, these being upgraded versions of the previous designs as well as being fitted with superheaters. All of them worked around Paris until 1934, when the decline in railway traffic made them surplus. Some ended up going back to the Nord before all of them fell under national ownership in 1938, continuing to work as goods engines around Paris and the north of France. France wasn't the only place these engines operated, as 12 engines were recorded being built by various companies in Belgium for work in China on the Peking-Hankow Railway. How these engines performed and how long they operated for isn't known. 10 were built for broad gauge in Spain in 1912, working between Cordova and Belmiz. These engines were said to have suffered much wear working on the gradients of the line, and because of their overall poor water capacity, had to tow a wagon fitted with a wooden water tank to keep their boilers filled. Despite this, they worked until 1947 before finally being withdrawn. The French Bousquet engines also had a decent working life, with most of them surviving until the 1940s. However, with the introduction of more powerful, conventionally designed locomotives, the Bousquets ended up being less powerful and more complicated to maintain than modern alternatives, and so by 1950, most of them had been withdrawn, with the last one being withdrawn and scrapped in 1952. Sadly, none were preserved. Gaston du Bousquet did design many other successful locomotives for use on French railways, but out of all of his designs, his name is mostly attributed to this one. Just goes to show that sometimes the work you'll be remembered for isn't always your best, sometimes it's your most unique. May I introduce you to the triplex locomotives? Steam locomotives built with a 2-8-8-8 two-wheel arrangement. These boasted 2 cylinders per bogie and had 24 driving wheels. They were long and slow, but without question powerful as hell. The first 3 were built for the Erie Railroad from 1914 to 1916 and could supposedly pull 650 freight cars. If my mathematics is correct, with the average freight car being around 55 foot in length, that means the engines could theoretically haul a train of freight cars roughly 6.7 miles long. An additional triplex was built for the Virginian Railways in 1916, with a 2-8-8-8 four-wheel wheel arrangement and was given the classification of XA. Despite their immense pulling power, these engines were primarily used as banking engines, helping push heavy freight trains up and over steep gradients. They could never achieve a high top speed, only averaging around 10 miles an hour, with the Virginian 28884 only ever hitting 3 to 5 miles an hour. But their line of work meant that speed wasn't a necessity. The engines also had a relatively poor capacity for coal and water, but as they were only bankers, they were never far from a coaling station or water tower. And yes, because the driving wheels were mounted under the bunker and water tanks, the engines didn't technically have tenders, making them some of the largest tank engines ever built. That's about where the praise for these engines ends, unfortunately, as they did have a few noteworthy drawbacks. Firstly was the boiler. Despite its size and steaming capabilities, it often couldn't produce enough steam to meet the demands of the cylinders. Again, they never had to travel far, so this wasn't a glaring issue, but it was still an issue nonetheless. Another problem was how the cylinders exhausted steam. The middle right and front set exhausted the spent steam through the smoke box as standard, but because the middle left and rear set of cylinders exhausted steam via an exhaust to the back of the engine, it meant the firebox had a poor draft, and as such, the engines had a problem with boiler heating. There weren't many other problems with the engines aside from these, but they were still enough to make the railroads not want to build any more. By 1933, all 3 of the Erie Railroad's triplexes were scrapped, and the one built for the Virginian Railways was taken apart in 1920 and converted into a 2880 and a 282. Both of which worked until 1953. Strangely enough though, a patent was granted in 1914 for a quadruplex locomotive, a 28882. The design meant it would have been roughly 129 feet long and weigh almost 400 tons. The design also featured an additional cab for the driver at the front of the engine, a flexible boiler, and 2 separate boilers served by one firebox. By the time the patent was granted, the flaws in the design of the triplex engines showed that making them even longer wasn't going to work. A quadruplex engine was built in Belgium, but to a much different design. A patent was also put in for a quintuplex engine, a 2888882, but this also never saw the light of day. A 21010101010 quintuplex, that's 50 driving wheels, keep up, was featured in Trains magazine in August 1951, however the idea was merely an artist's speculation and not an actual proposed design. And so that's the story of the triplex locomotives, another interesting example of how the extremely heavy rail loading gauge in America allowed engineers to design locomotives with no regard for weight limits or length, allowing us to truly see the sheer possibilities of rail locomotion. Just don't expect to see anyone building one anytime soon. Some locomotives are built to replace outdated designs, some are built for one-off jobs, and some are built to trial new technologies. In 1932, however, one engine was built in Belgium, seemingly not for any of the previously listed reasons, but simply because they could. Introducing Belgian State Railways number 2096, boasting 2 cabs, 2 fireboxes, 2 boilers, 8 cylinders, a total length of 31 meters and a total weight of 248 tons, it's fair to say that this Goliath of an engine was an absolute unit. On top of that, it used an 062 plus 24242 plus 260 wheel arrangement, which, put simply, meant it had 20 driving wheels and 10 unpowered guiding wheels, giving it the unique trait of being a quadruplex locomotive. It was basically 2 engines stitched together. Its length meant it had to be double-ended, as there was no way it would fit on any pre-existing turntables. It also gave the engine the title of world's largest steam locomotive, a title it held until the creation of the Union Pacific Big Boys. The boilers of the engine were both slightly skewed to allow firemen better access to the fireboxes. The fireboxes had a water wall between them to prevent them from getting too hot. The coal was stored in bunkers on one side of each boiler, and the boilers were positioned so that coal would fall under them to the fireman's side of the cab for easy access. The engine also had a driver's cab at either end of the main body to provide the driver with an easier time seeing ahead. On top of of this, the boilers had a unique system of their own, this being an early version of the Franco-Crosty boiler design. Exhaust smoke and steam from the cylinders and fire was routed through a feed water heater in the engine's water tanks, essentially preheating the water before it was fed into the boiler in order to help maintain boiler pressure and improve efficiency. The feed water heater was set up almost like an additional boiler, and given that each boiler had their own feed water heater, you could make the argument the engine had a total of 4 boilers altogether. The craziest part of all of this was that it actually worked. It developed roughly 3,000 horsepower and was so strong that its pulling power was limited by the strength of its couplings. It was limited to 60 km an hour while in service, and despite its length was able to traverse relatively tight corners with ease. So why did they build it? Well, frankly, nobody's really sure. It was well beyond anything Belgian railways needed at the time for goods work, and its limited speed meant it was practically useless for passenger services. Its sheer size, despite its dexterity, would have made storing it a hassle, and it's likely that with so many extra wheels, cylinders, joints and so on, it would be much more difficult to maintain. Not to mention the fact it required an additional person to help fire the second boiler. Quite frankly, the only reason I think of as to why is, why not? It was displayed at the National Exposition in 1935, but then taken out of service shortly after and put into storage. Some believe it was intended to be a proof of concept, as not long after, designs emerged for a bigger engine using a similar layout intended for the Russian market. This engine followed a 2442 plus 2882 plus 2442 hexaplex wheel arrangement for a total of 32 driving wheels. This, however, never seemingly made it past the planning stage. In 1943, the quadruplex was found by occupying German forces, who requested it be repurposed. It was essentially cut in half and converted into 2 engines. These worked around North Germany before coming into Russian ownership in 1945 and being sent to work in Poland. The last one to be seen working was at Krakow in 1955. Afterwards, nobody really knows what happened to them. The quadruplex then is perhaps one of the weirder engines to ever be built. Not only was it a quadruplex, a design that most railways saw as unfeasible to pull off, but it was also very powerful, surprisingly efficient, actually worked, and was built in, of all places, Belgium. It was far too overkill for Belgian railways, and the design was never really adopted anywhere else. Perhaps then the quadruplex should be remembered, not only as a bizarre machine, but also as a testament to the idea that sometimes the best response to the question of why is simply, why not? The Union Pacific big boys were pretty big, clues in the name, and by most are often referred to as the world's largest steam locomotives, myself and Google included. But what if I told you both myself and Google may be wrong, because there existed another 18 engines that could easily go toe-to-toe with the big boys? Formed in 1938, the Duluth-Mesabi and Iron Range Railway came about after the Duluth-Mesabi and Northern, Spirit Lake Transfer Railway, Duluth and Iron Range, and the Interstate Transfer Railway were merged into one company. Iron ore was the main traffic of the railroad, taking it from mines in Minnesota and Wisconsin to ports in the Great Lakes. The existing rolling stock of the lines was able to keep up with the work until 1940, where, thanks to the outbreak of the Second World War, the volume of iron ore the line transported practically quadrupled. Longer trains required more motive power, but rather than double-head their trains, the DMIR simply decided to build bigger engines. Needing something that could tackle steep gradients while pulling a heavy load, the DMIR ordered 8 engines from the Baldwin Locomotive Works, basing their design on the 2 882 engines used at the time on the Western Pacific Railroad, already some of the biggest and most powerful engines in the world. These new engines, however, would be fitted with an even bigger firebox, coal-fired, and a bigger, all-season cab for the footplate crew, necessitating an extra pair of trailing wheels be fitted under the cab, giving them a 2884 Yellowstone wheel arrangement. The first engine arrived in 1941, boasting 5'3" driving wheels, 4 cylinders, a total wheelbase of 113 feet, weight of 315 tons, a tractive effort of 140,000 pounds, and a top speed of 45 miles an hour. As a comparison, while not as large, heavy, or as fast as a big boy, these new engines could certainly overpower them. Its tender alone was capable of holding 26 tons of coal and 25,000 gallons of water, with the engine itself consuming 10 tons of coal and around 12,000 gallons of water an hour, making the engine not only powerful, but hungry too. To put it into perspective, a report stated that the amount of coal the engine burned in 1 hour would have been enough to heat a house for 2 winters. Compared to the previous Class M1 and M2 engines used on the line, these new locomotives were able to pull loads 25% heavier than their predecessors. Classified as M3s, the engines were found to easily handle the work they were given, exceeding the railway's expectations, and as a result, the DMIR ended up ordering 10 more locomotives, which were to be classified as M4s. Most railwaymen, however, referred to them as Yellowstones due to their wheel arrangement. As much of the iron ore traffic was seasonal, the engines saw less use in winter, and so when the new batch of M4 engines were completed in January of 1943, some of them ended up helping out on the Denver and Rio Grande Western Railroad until they were needed back on the DMIR. The Rio Grande seemed to adore these locomotives, with the railroad stating that they were some of the finest engines to ever run on their line. As such, the Rio Grande went as far as to lease the engines for use on their line again the following year, along with the Northern Pacific Railroad and the Great Northern Railway, though the Rio Grande quickly returned them after an air brake failure caused engine number 224 to wreck. The Yellowstones continued to work the line and proved to be invaluable to the railroad, each hauling millions of tons of iron during their lifetimes, but their strength wasn't enough to keep them running forever. After the war, many United States railroads prioritized dieselization of their lines, and the DMIR was no different. Steam engines were getting more and more expensive to operate, and so by 1958, after less than 20 years of service, the line began to withdraw their Yellowstone locomotives, with the last engine running in 1963. Luckily, out of the 18 built, 3 have survived into preservation, on display at the Lake Superior Railroad Museum and 2 harbors. It's still somewhat of a debate as to which engine is truly bigger. While the big boys had the lead in both weight and total length, the Yellowstones more than made up for it with their sheer power. It's a bit like Mike Tyson versus Muhammad Ali. We'll never truly have a solid answer, but the fun is in guessing, isn't it? That is until someone gets fed up and decides to restore a DMIR Yellowstone to find out. Here's hoping for a railroad rumble in the jungle. Railways have been around for a long time. Naturally, in times of war, attempts have been made to weaponize railways, and nothing was more effective on a railway than simply bolting a heavy cannon that would be otherwise impractical to move around to a flatbed and using the railway to push it about. Over time, these cannons got bigger, until eventually full-on naval-grade cannons were being mounted for use on railways. While effective for destroying long-range targets, their accuracy was often limited by the direction of the track, and they were very cumbersome to move around, often requiring tracks to be specially laid in order for them to hit a target. Despite this, the ability to move such a powerful weapon was worth the trouble it took to prepare it. That brings me on to the subject of today's little factoid. In 1934, the German Army High Command wanted a weapon that could destroy the defences in place at the Marino Line, France's main line of defence from Germany. They wanted the gun to be able to fire shells powerful enough to penetrate meters of thick reinforced concrete while far enough away from the front lines to be out of the range of French artillery. Krupp of Essen, one of Germany's most prolific engineering companies, was set with the task of designing and building the weapon. Engineer Erich Müller calculated the gun would have to fire a shell roughly 80 centimeters in diameter and nearly 7 tons in weight. As the company had other projects to attend to, the weapon was somewhat put on a back burner until 1936, when, during a visit to the works, Adolf Hitler inquired about how feasible such a weapon would be. No definite answer was given, but the Inquisition did lead to the project taking up a priority spot in the company. By early 1937, the designs for the gun were finalized and construction of the weapon was set into motion. In order to fire the desired shells, the main barrel of the gun needed to be 32.5 meters long, with an equally large frame to mount the gun onto. Due to the complexity of fabricating a single barrel of such a size, the actual cannon part of the weapon wouldn't be completed until 1940. In the meantime, a test model was built in 1939 and trialled at the Hillersleben Proving Grounds. There, it managed to fire a 7-ton shell through 7 meters of concrete and 1 meter of solid armor plating. Pleased with the results, 2 of these cannons were ordered by German High Command. Once the first gun was completed in 1941, it was properly trialled in Różanwałęd, now Darłowo, Poland, where the gun was found to have an effective range of 39 kilometers, with a maximum range of 47. To put that into perspective, it could have easily hit the cliffs of Dover or even a target halfway to London from Calais in France. Once the trial was deemed successful, the cannon and its newly fabricated chassis were packed up and shipped off to battle in 1942, having been given the name Schwere Gustav or Heavy Gustav, named after the senior director of the firm, Gustav Krupp. As France was already under German occupation, the gun was sent east towards Russia to aid on the Eastern Front. The gun arrived in Crimea to aid the German forces during the siege of Sevastopol. Before the gun could be assembled and fired, however, the German forces had to lay down a short section of railway line connected to the main line they were using to transport Gustav. This not only included the rails Gustav would be sat on, but also additional rails for the cranes required to assemble the gun to rest on too. It took 4,000 men 5 weeks to lay down the rails, assemble the gun, and get it into firing position, requiring a crew of 500 men alone to operate and fire it. Once assembled, the world was introduced to the force of nature that was Schwere Gustav. The entire construction had a total length of 47.3 meters, a height of 11.6 meters, and weighed a total of 1,350 metric tons. To put that into perspective, here is a human being. Here is the Flying Scotsman. Here is a Union Pacific big boy. And here is Gustav. These were the shells it was firing, which weighed 7 metric tons each. The average male African bush elephant weighs 6 metric tons. Long story short, this thing was a mobile building that had the power to fire an earth-shattering payload as heavy as an elephant over 40 kilometers away with relatively sharp accuracy. It was truly a force to be feared. The siege had been going on for months at this point, with Soviet forces managing to hold control over the city thanks to the many underground bunkers and fortifications they had. Conventional assaults as well as aerial and naval bombardments proved to be ineffective against the reinforced bunkers and forts, and so it was up to Gustav to destroy these fortifications, something it was more than equipped to do. The gun was used from the 5th to the 17th of June, firing a total of 47 rounds. By the 4th of July, the siege was over, and Sevastopol was practically razed to the ground, with most bunkers, underground or overground, effectively destroyed. The Gustav was then dismantled and moved on to the Eastern Front, being assembled roughly 30 kilometers away from Leningrad, ready to be used to help storm the city. Despite the gun being good to go, the attack was cancelled, and the gun remained there until early 1943. Meanwhile, the second cannon, named Dora after the senior engineer's wife, was positioned outside Stalingrad in August of 1942 and fully assembled by September. also positioned with the intention of aiding in an assault on the city. Back in Germany, the development of another railway gun was well underway. Known as the Lange Gustav, this gun would have had a longer barrel than the Gustav and fired a narrower caliber of shell intended for longer distance, giving it an effective range of 190 kilometers. In a poor turn of fate for the Germans, the cannon was severely damaged during construction thanks to several bombing raids made by the RAF. At this point, it isn't entirely known what happened to either of the cannons, as neither of them were used again in combat. After the assault on Leningrad was called off and the harsh winter of 1942-43, it was likely that Allied forces were able to retaliate and push the German armies back. By this point, the war was turning against the Germans, and as such, both the Gustav and Dora were dismantled and moved back towards Germany. Because of how long it would take to set either of them up, Gustav or Dora couldn't be set up in time to act as a defense against the advancing Allied forces, and even if they could, they were built to destroy bunkers, not small, mobile targets like advancing convoys or aircraft. On the 14th of April 1945, the Gustav was destroyed to prevent it from being captured by the approaching US troops, with its remains being found 8 days later by said US troops in a forest roughly a few kilometers away from Zwickau. Dora was blown up shortly afterwards on the 19th, also to prevent it from being captured. Debris from both guns was taken and studied by Soviet engineers, but little useful information was gained from it. As large and impractical as they were, Gustav and Dora were both frighteningly powerful weapons that luckily never got to fully show off what they were capable of. I remind you, these things could easily pierce a 7-meter thick reinforced barrier from 39 kilometers away. Overall, while it wasn't the only terrifyingly powerful weapon the Germans were packing, we can be thankful they were at least underutilized. Because to be able to annihilate a target from so far away much better than the Air Force could, well, let's just say that it's certainly a frightening example of German engineering at its most brutal. Australia is a big country, and as such requires a lot of power to traverse. By the late 1920s, it became clear to Victorian Railways that their Pacifics, despite their impressive size, just weren't quite enough to keep up with the work put upon them, and as such decided what they needed to do was go bigger. By 1923, the increase in passengers travelling with the Interstate Express to Surbiton and Albury was taking its toll on the engines of Victorian Railways. The services had to be double-headed by two A2s in order to keep up with demand and to traverse the steep and sharply curved lines between Melbourne and Ballarat. As such, Victorian Railways put plans in place to build a fleet of engines capable of hauling these expresses on their own. Their initial plan was to develop a 482 mountain-type locomotive. However, these plans were put aside after the S-Class Pacific engines were introduced and had taken over running the services by 1928. Despite their performance, the S-Class engines still struggled along the tricky line, and so interest in the mountain engines picked up again. By 1936, Victorian Railways finalised the requirements for the engine, and the railway's engineers set about designing it. The design they came up with was now a 484 instead of a 482, and would be fitted with plenty of modern comforts for the crew and to help boost performance. Construction of 3 of these engines began in 1939, but was quickly halted due to the outbreak of war. Priorities quickly shifted elsewhere until it was decided that these engines would be ideal to help with the increased wartime railway traffic. One was completed in February in 1941 and quickly put to work. Classified as H220, the engine boasted 3 cylinders, a mechanical stoker, roller bearings, load-compensating brakes on its tender, power-operated reversing gear, American-style bar frames, duplex blast pipes, a tractive effort of 55,000 pounds, and, including the tender, a total weight of 260 tons, making it the biggest non-articulated steam locomotive ever to run in Australia. Once fully assembled, it was found the engine was too heavy to traverse the line it was intended to work on, and that multiple bridges would need to be strengthened to accommodate it. The only line that could accommodate the engine was the northeastern line to Albury, and so it was put to work there. It was primarily used to move fast goods, despite being designed for passenger work. network. However, it still got many chances to haul express passenger services and the odd troop train when needed. On occasion, it found itself pulling the Spirit of Progress service from Melbourne to Albury, where it managed to outperform the Pacific engines that usually hauled the service. On one occasion, it was noted that the engine managed to clear Glenroy Bank, a 5-mile-long gradient of 1 in 50 at a speed of 45 miles an hour, a climb that the usual Pacifics could only make at 15 miles an hour. Further testing in 1949 recorded H220 as having a top speed of 50 miles an hour, a drawbar tractive effort of 52,000 pounds, and the ability to produce 3,600 horsepower. While not the fastest of engines, its power output remained unmatched by any modern diesel or electric engines in Australia until the introduction of the National Rail NR class, introduced over 50 years later. The engine's size and incredible power led to many railwaymen giving it the nickname of Heavy Harry. Eventually, the engine settled into running fast goods services between Melbourne and Wodonga, as not only was it capable of pulling heavier trains over the steep gradients of the line, but its large tender also meant it only had to make one stop for water during the run, whereas the other engines would have to make 2 stops for both water and coal. Despite the engine's success, wartime restrictions meant the other 2 H-class engines were never completed, and with the railway turning its attention to diesel traction by the early 50s, the railway felt no need to build any more, leaving H220 to be a one-of-a-kind engine. While most one-off engines often have a short running life due to them requiring non-standardized parts or having irregular servicing needs compared to other engines, Victorian Railways decided to just keep running H220 on mainline services, often using it for publicity, with some magazines calling it Australia's mightiest engine. Even without its publicity, Harry's sheer power was enough for the railway to keep it operating. Publicity and pulling power unfortunately wasn't enough to keep Harry running forever. By the mid-1950s, Victorian Railways was looking to heavily invest in the railway's infrastructure, and diesel and electric engines were being considered. VR had a massive backlog of maintenance work, and the upgrades to multiple lines required to allow H220 to run on them came low on the list. Despite the diesels at the time not having anywhere near as much pulling power as Heavy Harry, the fact they were lighter in weight combined with their ability to run as multiple units, meaning 2 engines could be operated by 1 crew, meant they could outperform many other locomotives, and the railway wouldn't have to spend money on upgrading the line to support their weight. As a result, diesel traction soon took over, and in 1956, Harry was withdrawn and put into storage. In 1958, it was officially taken off the Victorian Railways Locomotive Register. Fortunately, it was soon taken under the ownership of the Australian Railway Historical Society, who recognised its significance and moved it to the Newport Railway Museum in 1962, where it has since made its home as one of the star attractions. Looking back, H220 is somewhat of an anomaly when it comes to locomotive designs. Not only was it too heavy for many of the lines it was intended to run on, but it also suffered many of the drawbacks that came with being a one-of-a-kind design, such as complex maintenance and awkward mechanical needs. Despite this, its sheer power and reliability proved to be more than worthwhile for the railway, giving it the chance to establish itself as one of Australia's most powerful steam locomotives. Just goes to show that, once again, even if a little overweight, there truly was no job steam power couldn't do. Streamlined steam engines are an icon for many railways. Not only were they stylish, but they also headed fast, important express services and were often the flagship engines for many companies looking to impress passengers. Out of all of these streamlined engines, however, one stands out among the rest as not only a massive mechanical marvel, but also because it was double-ended. In the 1930s, France began to heavily invest in their colony in Algeria, looking to improve much of their established infrastructure, including the railways. The line between Algiers and Oran was one such line in need of help as it traversed the Atlas Mountains, resulting in many sharp bends and steep grades of up to 1 in 38 along the route. Express trains had to be double-headed in order to make the journey, and the tight bends meant that they couldn't just use a bigger engine without risking it derailing. What they needed was a locomotive that had the power of 2 engines to tackle the grades while also being flexible enough to negotiate the bends. And soon, they found it. While not the most popular design at first, the Garrett engines built by Bayer Peacock and Company had become quite popular on many railways in Africa, proving to not only be powerful, but also flexible and quick when they needed to be, with some clocking speeds of up to 90 km an hour. They were primarily used as goods engines by many railways, but it wasn't uncommon for them to pull heavier passenger services too. Deciding that a Garrett was exactly what they needed, a prototype was ordered from Société Franco-Belge in northern France, who were associates of Bayer Peacock and Company. The engine was designed to have a 462/264 wheel arrangement, essentially being two Pacific engines in one, and in 1932 the prototype was completed. This monstrous machine, given the class of 231-132AT, was equipped with four 490mm cylinders, 1,800mm driving wheels, a mechanical stoker, Walschaerts valve gear, was around 27 meters long and weighed a whopping 195 metric tons. It was trialled in France before being sent to Algeria, with many officials being impressed by both the size and performance of the machine. In Algeria, it was put to the test on the lines between Algiers and Oran, where it really got its chance to shine. Where before, two engines would struggle to haul an express through the mountains, only one Garrett was needed, and despite the Garrett's reputation as heavy freight engines, it still managed to maintain express speeds. After modifying and fine-tuning the engine, an additional 29 were ordered and built between 1936 and 1941, with the newer engines, classed as 231/132BTs, being even bigger at 29.37 meters long and weighing 211 metric tons. The Walschaerts valve gear was replaced with Cossart valve gear, this uniquely being operated electrically instead of manually. Not only were they powerful, but pretty too, with the new engines having both their front and rear ends fitted with streamlined cases to reflect their nature as modern, up-to-date express engines. Once these engines came into service, they proved to be more than capable of hauling trains between Algiers and Oran alone, averaging speeds of 100 km an hour. On occasion, they were even known to run at 130 km an hour, the fastest speed ever set by a Garrett locomotive. This impressive performance led to them occasionally working expresses between Algiers and Constantine too, it being noted that they were able to shave 2 hours off the journey compared to the engines that usually ran the line, all while hauling a heavier train. These streamlined, double-ended monsters proved themselves to be unmatched express performers, and were possibly some of the most powerful express steam engines in the world. However, they still had their shortcomings. The Cossart valve gear was complex to maintain, with the reversing mechanism being a frequent source of grief for both drivers and repair crews alike. The size also proved to be somewhat of an issue, requiring some engine sheds and turntables be extended in order to accommodate their extreme length. On top of that, the quality of the water used in the engine's boilers was poor, which, combined with the lack of boiler maintenance, led to many of them steaming poorly later on in life. What really brought about the end of these engines, however, was the outbreak of the Second World War. Their frequent use on heavy passenger services, combined with the lack of maintenance they received thanks to the war, caused them to become worn out much quicker. As a result, by the end of the war, the engines were in a very poor state and in dire need of extensive repairs. In 1951, the decision was made to electrify many of Algeria's railway lines and introduce diesel power in the meantime. This, combined with Algeria starting to fight for independence, left the Garretts at the bottom of the priority list, and by the end of 1951, all of them were scrapped. When most rail fans think of streamlined engines, they often tend to think of your typical Gresley A4s or the New York Central Hudsons. But despite their maintenance-heavy nature and relatively short working life, I think you'll agree that their speed, power, and striking appearance makes the 231/132BTs certainly worth remembering too. By the 1980s, steam power had become redundant on many railways across the world, with most running diesel engines or fully electrifying their lines. Some engineers, however, still felt that steam was a viable option, and tried their best to prove that steam power could keep up with the times. In South Africa, this resulted in an engineer trying to beat out diesel power with a little help from a devil. Built in 1953, the Class 25s of South African railways were hard-working beasts, and for their time quite intricate in design, being some of the most modern steam locomotives in the world, fitted with condensing equipment to help them save water. They weren't without their faults, however, having a long history of needing to be modified and various features be replaced to keep them in working order. By 1973, the condensing equipment was considered too awkward and expensive to maintain, along with several other aspects of the engine's design, so it was decided they'd be rebuilt in order to make them cheaper and easier to run. At the time, South African railways wanted to transition from steam to diesel and electric engines. However, David Wardale, who was employed as a mechanical engineer on the railway, disagreed. He felt that steam power could still be drastically improved, and that because South Africa had such a plentiful supply of coal, it made more sense to use steam over diesel engines, with the price and availability of imported oil fluctuating. The railway held little interest in Wardale's ambition, but permitted him to trial his ideas when he promised they'd help reduce line-side fires. Wardale chose a Class 19D engine, number 2644, which was a notoriously bad performer, and had it fitted with better cylinders, better blast pipes, some other minor upgrades, and his secret weapon, a gas production combustion system, or GPCS for short. The way a traditional locomotive firebox works is coal is spread over a large grate. Once lit, the heat from the fire draws air up through the grate and into the firebox, helping the coal burn. A flammable gas is released from the burning coal, and opening the firebox door allows more air into the firebox to help this gas combust. The heat and burning gases are then drawn through the boiler tubes to heat the boiler before being exhausted out the smoke box. The problem with this system is the rapid rate at which air is drawn through the firebox often resulted in smaller, unburned pieces of coal getting pulled through the boiler and exhausted out the chimney. This not only meant that the engine was essentially wasting unburnt fuel, but the small particles moving at such a high speed effectively sandblasted many internal parts of the engine, causing a significant amount of wear on components. Not to mention that firemen had to maintain a thin bed of coals at all times when firing an engine. But too thin wouldn't produce enough heat, while too thick would stress parts of the firebox from the heat. As it was the gases that were released from the coal that produced most of the heat an engine needed, the gas producer combustion system worked by prioritizing releasing the gases from the coal and combusting it afterwards. The firebox grates had much smaller air holes to limit the amount of oxygen that got to the fire, and a nozzle would spray a small amount of exhaust steam from the cylinders up into the bed of coal. The coals were laid thicker, burned at a lower temperature, and the water combined with the slower airflow ensured that little to no unburned coal would be drawn through the boiler. Above the layer of coal were vents that allowed fast-moving air to enter the firebox and allow the released gases to combust. The hot gases would then flow through the boiler and then be exhausted as normal. This was a much more efficient way of burning coal, as not only did it ensure little to no fuel was left unburned, but the airflow ensured that no coal particles were flowing through the boiler and damaging components, or that any hot coals were being spat out causing line-side fires. An added bonus was that this layout also helped reduce the amount of clinker that built up at the bottom of the firebox. Once overhauled and after a few weeks of tuning, the modified 19D was found to not only be more powerful than its unmodified counterpart, but consume between 20 to 25% less fuel on average too. Footplate crews ended up nicknaming the engine Spooky, due to its unearthly performance and its quieter than usual exhaust. Deeming the experiment a success, South African Railways allowed Wardale to continue with his plan and modify one of the previously mentioned Class 25s. feeling that if he can modernise what was already seen as a modern steam locomotive design, then the railway might also see the same untapped potential in steam as he did. Engine number 3450 was selected and taken to the Salt River Workshops in Cape Town in 1979, where Wardale spent the next 2 years refitting it, not only with a GPCS, but many other minor alterations, including but not limited to a self-cleaning smoke box, better superheating, better cylinders, and a new feed water heater. The Vollschwarz valve gear itself was improved using measurements calculated on a computer. That's how up to date the engine was. On the 5th of February 1981, the engine was steamed for the first time, and after dealing with some leaks, the engine went for its first test run the next day. 3 days later, on the 9th, the engine was unveiled to the public, being given a bright red coat of paint and named LD Porter, after an Argentinian locomotive engineer who inspired many of the changes Wardale had made to the engine. The local press took a great interest in the locomotive, and by the end of the week, newspapers printing pictures of the engine had dubbed it the Red Devil. Its paint job, however, wasn't the only thing that earned it its nickname. Like the modified 19D before it, 3450 was found to be very fuel efficient, with savings of 28% on coal and 30% on water usage. Not only that, but the engine's overall pulling power was significantly stronger too. During tests, it was found that the dynamometer car used to measure the engine's power was faulty, and so most estimates of the engine's power were very conservative. Despite the skeptical measurements, the engine showed a 43% increase in drawbar horsepower at minimum, so it's possible that the engine was much more powerful than it was measured to be, while already being significantly more powerful than the rest of the Class 25s. As a result, the engine was officially reclassified into a Class 26, being the only locomotive of its class. All of this, paired with its size, really puts into perspective how absurd this engine was. The locomotive itself weighed 117 long tons, including the tender was over 90 foot in length, and had a starting tractive effort of 52,000 pound-feet. To put that into perspective, it was longer, heavier, and more powerful than a Gresley Pacific, while running on narrow gauge 3-foot 6-inch rails. I think you'll agree that, on top of being an absolute unit, the name Red Devil was certainly earned. So much so that a nameplate reading Red Devil was fitted to its smoke deflectors, making the name official. There was, however, a devil in the engine's details too. Many footplate crews found the engine awkward to fire, with the locomotive's performance often depending on the quality of coal available. The lack of air holes also caused problems with ash building up on the firebox grate. A leaky superheater and temperamental boiler pump didn't do it any favours either, but its biggest drawback was its lack of traction. The Class 25s often suffered from wheel slip, especially when starting on or climbing grades, and Red Devil was no different. Even with better sanding gear, it just couldn't seem to overcome its problem with adhesion, essentially rendering all that extra power it had useless if it couldn't deploy it in any meaningful way. But in the end, it wasn't any of these little foibles that ended up condemning the project, but simply South African Railways' indifference to the engine altogether. The directors by this point had made up their minds, and wanted to make the switch to diesel engines no matter how efficient steam power was by comparison. Wardale left South African Railways in 1984 once he realised the railway was steadfast on scrapping steam power, and moved on to other projects. Red Devil ended up being modified and partially converted back into a standard Class 25 to help resolve some of its issues. It was later withdrawn from service, but saved from scrap by a group of preservationists, who used it to pull special excursions until 2004, when it was eventually put into storage. It was recently restored into working order in 2018 and has since been carrying excursion trains during the South African winter. While certainly not the last great hurrah of steam power, the fact that Wardale was able to improve the performance of an engine so much just goes to show that steam locomotives might still have more to give than we first thought. Just be sure to practice your fiddle playing before you go about building another engine. You know, just in case. Subscribe for more.